Week of the program and the even more exciting penultimate lecture from Mark Dennis from the University of Bristol with this topic, Vikings in shades. Shades are sunglasses, are they?
Yes, well, as in the picture.
Navigating by skylight polarization.
Okay, well, thank you, Keith, and let me just put the... I'd like to thank all the organisers of the programme for such an exciting time, certainly in the last couple of weeks that I've been here. And when Keith asked me to give a talk in the final week, I thought I could talk about some of the more complicated topology and the complicated optics that we do in Bristol, but I thought maybe instead a topic like this, which I normally give a version of as a popular lecture to undergraduates, might be a little bit more amusing for the last week of the programme. So my title is Vikings in Shades, and this is my illustration. In fact, it is not an original Viking helmet. It is actually a custom-built Boba Fett as a Viking helmet, for those of you who know Star Wars. So the idea, the hook, is about the Viking navigation. And of course, Vikings were one of the first set of early civilization who travelled extensively out of sight of land, more or less due east-west between Norway and the coast of North America, and they did not have knowledge of a magnetic compass. So the question is, how did they know that they were going in the right direction, because they might have ended up going in the wrong direction? And the usually accepted argument is that Vikings took their bearings from the sun with what is called a wooden sun compass. And this is an artifact that was discovered in Iceland in the 1930s, which is, I guess it's like a sundial. See lots of examples of these around Cambridge. So we have a gnomon that sticks out, and it sets a shadow, and the various different directions of the shadow are scratched out as hyperbolas on the surface of this sundial. Yes?
Can I ask you a precision? Because what does it mean going in the right direction? I can think that they were not knowing where they were going first.
Right. But they had, for example, an established
already okay.
These places.
Yeah.
We're not talking about explorers. We're talking about the rest of them.
Okay. They wanted to go to this precise location. Okay.
And of course, if you're off by a couple of degrees, you'll miss it. So it requires some.
I'm thinking you were talking about the very first one, but we were just going in front of them, and this is it.
So one of the things, of course, that we have to assume then is that the Vikings had a rather accurate way of telling the time. Because, of course, we usually use sundials to tell the time from the shadow from a known orientation. Whereas if they're trying to get the orientation from the shadow, they had to have an independent way of telling the time. And I'm not going to discuss how they did that. Today, we're going to just assume that if we know the position of the sun in the sky, then we can determine accurately direction. And of course, if you're stuck out in the middle of the ocean, there aren't many other things that you can take your direction from other than the direction of the sun. But the problem is, as we're very familiar with here on the east coast of England, visibility in the North Atlantic region is often very poor. And so the sun itself might be obscured by cloud or fog. I think today we're in luck. There is a visible sun on the other side of the building, but in general, that's not the case. So the question is, how would the Vikings have been able to have taken their orientation on a day such as this, where you can more or less see the sun hiding behind that cloud, but you could easily imagine if it was there, you couldn't tell it directly. And so the question is, and this had been bothering archaeologists for much of the 20th century, how might it be possible, using just visible light, but not exactly the sun, to tell where the direction of the sun is, assuming that given that they can take their orientation. And the theme of my talk is based around a hypothesis which comes from a well-known fact, namely that the light of the blue sky is polarized. And I can even do a demonstration because I have some blue sky just out here. So you can see if I turn this polarizer, there's that's lighter and that's darker when I turn it by 90 degrees. It's a bit, the windows are a little bit polarizing as well, but you can see there's definitely a change. If you look at the background of a cloud, the luminosity of the cloud does not change. Anyway, you can come and have a look at some of these later on, and here is out of my window in Bristol just to see what's going on. So the line on the polarizer represents the direction of vibration of the light that the polarizer passes. So the idea is there is some background vibration direction which is like this, and it, by Malice's law, is just makes a cosine, the intensity is a cosine, or cosine squared, of the angle that this orientation of this polarizer is making with the background polarization of the sun. So all that the Vikings would need then would be a pair of sunglasses, shades, and if they were to turn these shades, they would be able to work out what the orientation, the direction is of the polarization, and the direction of the polarization depends on the direction of the sun. Roughly, the pattern rotates rigidly with the sun as the sun rises and sets. So if this is the direction of polarization in the sky, pretty much the direction of the sun is at right angles to the direction of the vibration. So, and it certainly is that if you were to look at the zenith straight up. So the argument, look at the zenith, look for the most dark direction, have a line drawn on it, and you can tell where the sun should be. It doesn't matter how high the sun is, all that matters is the azimuthal angle of the sun. So, I'll talk a little bit about this controversy. I'll explain how it works as a little bit of, well, hopefully for many people, revision of classical crystal optics. But what I want to emphasize, and the original side of this work is emphasizing the geometric approach to these optical phenomena. They'll tell you how to do it, or how it's been proposed by some amateur navigators, and then the main meat of the mathematics is actually to look at the skylight pattern in more detail, having built up some of this geometric approach. So the story really begins with the realization in the 1940s that skylight is used, or polarized skylight is used for navigation throughout the natural world, not only by Vikings, but also by bees and birds and many other organisms. And von Frisch, who got the Nobel Prize for Physiology or Medicine in 1973, wrote this in his Nobel lecture, which is almost a sort of manifesto for this topic. The bees must have been able to read the sun's position from the blue sky. The direction of the vibration of polarized blue light differs in relation to the sun's position across the vault of the sky. Thus, to one that is able to perceive the direction of vibration, even a spot of blue sky can disclose the sun's position by its polarization pattern. Are bees endowed with this capacity? Then he describes an experiment that he did with a beehive and a sheet of polarizer, and he rotated it, and lo and behold, the bee's orientation followed the direction of polarized light, rather than, for example, the direction of the sun. So the bees are able to perceive polarized light. The sky, which to our eyes is a uniform blue, is distinctly patterned to them. They use this extensively and in their orientation guide themselves not only by the sun's position, but the resulting polarization patterns of the blue sky. Once again, bees appear to us miraculous, but it is now clear that ants and other insects, crayfish, spiders, and even octopuses perceive polarized light and use it for orientation, and that among all these animals, the human being is the unendowed one. There is research that we do have a residual polarization sensitivity known as Heidinger's brush, but it's not clear that this is ever something that we evolved from an evolutionary viewpoint. And so effectively we can't see polarization, but it's extremely common across the natural world. And for example, birds use it for their long-term navigation, exactly the way that we're discussing Vikings doing it. So The skylight is the degree of polarization varies, the strength of the brightness to darkness as we rotate the polarizer, but it's quite strongly polarized along the arc in the sky at 90 degrees to the sun. And the direction of polarization is more or less perpendicular, or it is exactly perpendicular to the direction of the sun at the zenith, straight up, and everywhere else it's approximately perpendicular to the direction of the sun. I can draw a great circle. This is a fisheye projection, so this radius here is equal to theta coming down, and joining the great arc more or less takes you to the direction to where
what is the physics of this polarization? The sun's rays.
I'll be talking about that later. I'll come on to that. So what I'm going to do is I'm going to talk first about the fact that this is there, how to discuss with crystals, and then it turns out understanding how crystals do it, it maps very nicely onto how the sky does it itself. So the original suggestion came from, in this magazine, Skalk, which is a Danish archaeology magazine. And this was an article by Ramsco in 1967, and I was actually able to access the original in the university library, which has got this charming picture of a Viking trying to work out what the direction of polarization is. So the original hypothesis that Vikings navigated in cloudy skies by skylight polarization using sunstones, these objects that had mystified archaeologists for a long time, they're mentioned in Icelandic sagas as devices that somehow magically reveal the direction of the sun. But no one knew what they were. And more recently, in 2006, Leif Carlson wrote this article about how he was able to navigate on the open sea using sunstones, polarized light, and other sorts of techniques reconstructed from the Vikings. And he proposed a method with a transparent birefringent crystal, classic calcite object from physics labs, whose old name is Iceland spar and commonly occurring in Iceland. Ramscow himself thought that the crystals the Vikings used would be actual polarizers, like we've just described, but those are very uncommon in the North Atlantic, whereas this Iceland spar is very common. In fact, Carlson wrote this book, Secrets of the Viking Navigators, how Vikings used their amazing sunstones and other techniques to cross the open ocean. And if you're interested, I believe today is the last post for Amazon for Christmas, describing this technique. But in a way, what can we contribute as scientists? Well, it's a bit like this expedition in the 1960s of Thor Heyerdahl, this Kon-Tiki expedition. We're not in a position to judge how archaeologists work, but we can at least discuss whether or not it's possible. And there has been a lot of debate in the literature. Here's a paper in Applied Optics from 1994 disputing Viking navigation by polarized skylight. Here's the abstract, and in particular the keywords: light scattering, skylight polarization, Viking navigation, and scientific gullibility. So these people weren't convinced, but in recent years it has become quite a fashionable subject again. So these people, who are primarily biologists, have used their polarimetry setup, usually used to detect how animals detect polarization of sky, to ask whether the Vikings could have navigated even under foggy and cloudy conditions, not just needing a patch of blue, but whether you can actually figure out what's going on behind clouds. And just this year, another paper in Proceedings of the Royal Society A depolarizer as a possible precise sunstone for Viking navigation, which details more detailed measurements trying to reconstruct the sort of setup the Vikings may have had. So the historical evidence is, well, this is from the original Icelandic saga, and for those of you not fluent in medieval Icelandic, here's a translation. The king made them fetch the solar stone, held it up, and saw where light radiated from the stone. So that's the evidence that we're going on. But interestingly, a piece of birefringent crystal, just like this, believed to be calcite, was discovered in an Elizabethan shipwreck from 1592 off Alderney in the UK Channel Islands. And no one was able to explain what this chunk of crystal was doing on an Elizabethan ship. The guess is that these were actually well-known but not written down techniques for navigation. And although in 1592 they had the magnetic compass, this particular ship was a gunship and had lots of ferrous cannon on, and so that would have distorted the direction of a magnetic compass. So this is a guess that maybe this was still part of the same technique. But then the question is, how might a sunstone actually work? Because if we see the polarizer, it's clear and obvious how we might use it, but the whole point about a transparent crystal is it's transparent. Mathematically, it's a unitary operation, not a projection. So how can we make a measurement using an object like that? And that's what I want to talk about. So this calcite is transparent mineral, does not obviously polarize light. But calcite is birefringent, and it gives it different polarization properties from a polarizer. And that's what I will talk about, which may or may not be revision. For some of you, the idea of crystal optics was a mainstay of undergraduate physics for many decades, but I think has more or less fallen out in the last few years, so many people don't actually see this. So crystal optics is a very good way of understanding sort of the textbook electromagnetism, such as patterns like this. So what we're interested in is light beams propagating in a material like this, and in the ideal world it's linear material, it's dielectric, but it's anisotropic, so it's different for light propagating in different directions. It's not absorbing, that would give it colour, and it has no chirality, so there's no optical activity. And what we have is we've got two vectors, the electric field E and the so-called displacement field D, and because it's linear, they're related by this matrix equation where this epsilon r is the dielectric tensor. And the fact that this is a tensor represents the fact that different directions are treated differently. And because of these properties, our tensor is real, invertible, and symmetric. And just as a quick recall, if we're going to think about it geometrically, a real invertible symmetric matrix, the way it acts on a circle in 2 dimensions is to give us an ellipse. And in general, this V would move to U, but would not change along either of the ellipse axes, which are the eigenvectors. So when polarized light enters a crystal, and I can actually show you what actually happens with birefringence. So here is a crystal, and I've put a little blob of blue tack on the back of it, used to stick pictures up. And I've put here, the blue tack is now at the top face of the crystal, and you can see, well, there's one here as a line, and here as a dot. But if I turn the crystal over, you can see that there are actually 2 versions of the dot, not one. And this is birefringence in action. The light going through the crystal has split into 2, has diffracted twice. And these are polarized. If I turn my polarizer, you can see it switching from one to the other.
Oh, wow. That's really cool.
So this is, well, certainly this is the sort of thing that, well, even now stimulates physics undergraduates to take their electromagnetism lectures seriously. So what happens, the polarization of the light going in is resolved into 2 orthogonal eigenpolarizations, and each of these words is a separate one of these images, these rays. Each eigenpolarized ray propagates in a different direction, so they look like they're in different places, owing to what's called beam walk-off. And we get patterns like this with these fringes, and the fringes come from the fact that each eigenpolarization propagates through the crystal with a different refractive index. And this is the way, for example, that people can study all of these complicated defect textures in liquid crystals, for example. Liquid crystals are inhomogeneous. I'm only going to be talking about the homogeneous case. So we have to now get a little bit technical with Maxwell's equations, but it's very straightforward. We're only thinking about plane waves propagating in the crystal. And the crystal has no free charges or currents, so I'm thinking about E, D, B, and H. As plane waves, they're all proportional to propagation direction S with wave number k and frequency omega. If I write Maxwell's equations assuming a solution of this form, it's effectively like writing Maxwell's equations in Fourier space. I can replace all of my occurrences of del with IKS and all my time derivatives with minus I omega. So div d equals 0 becomes s dot d equals 0. So it's our d vector that's perpendicular to the propagation direction in the crystal. B is also perpendicular to propagation in the crystal. Normally B dot is curl E, minus curl E takes this form, and the other one involving D and H takes this form. So we choose to work with D because it's D that's perpendicular to S, not the electric field, but the displacement field. The electric field is perpendicular to the direction of energy flow, which is the cross product of E and H. So just using these equations, we can now derive an equation for the D, which is proportional to this plane wave. So D, where's D? It's here. So D is proportional to S cross H. We assume the material is non-magnetic, so H is proportional to B. B is here, so I can substitute again, and I get minus S cross E. And E was this tensorially related to D, so finally I have this constant minus S cross inverse epsilon D equals D. So it's a linear relationship for the vector D. So this tells me that a plane wave solution of Maxwell's equations propagating in the crystal is going to have a polarization D0, which satisfies this equation. And this equation is actually just the equation for, well, this operator minus S cross is just projection into the plane perpendicular to S. So it's like, well, I call it the looking operator. We have a line of sight, and whenever you look at something, you always are looking at it in the plane perpendicular to the direction you're looking in. And that's all that we have here. So plane wave solutions of Maxwell's equations follow if we just can solve this equation, my eigenequation, D0 with this operator projection into the plane perpendicular to S, sandwiching on each side this tensor equals, well, reciprocal squared of the refractive index times D0. And that gives us our polarizations. So this is the transverse looking operator, and if epsilon inverse is represented by an ellipsoid, then we just take our ellipsoid and project it into the plane perpendicular to our looking direction. And what do we see when we project that? We actually see an ellipse. And the two polarizations are the two axes of that ellipse, projecting perpendicular to the line of sight. And as we change our line of sight with respect to this tensor, these two directions will change. And this gives the distinction between what are called uniaxial and biaxial crystals. Uniaxial crystals, well, the number of axes are what are called the optic axes. They're not the geometric axes of the eigenvectors, which are here. They're the directions S, where this transverse looking operator has two equal eigenvalues. So for uniaxial crystals, a uniaxial crystal corresponds to an ellipsoid of revolution. In an ellipsoid of revolution, one of the directions is always along the projection of this one axis here. So then if I look down the axis, the projected ellipsoid looks circular, and looking circular exactly when I can't decide what the two eigenvalues are equal. Eigenpolarizations. biaxial crystals, in general, I've got two different optic axes. This is a general ellipsoid, but represented in terms of optic axes, my rank 2 symmetric tensor is just the symmetric product of these two vectors u and v. And the u and v vectors give, if you look at them along the direction, project perpendicular in the plane perpendicular to that direction, again you get a circle, and that circle corresponds to this degeneracy. So when we talk about biaxial crystals, we always have in mind not the eigenvector decomposition of the tensor, but instead this symmetric product representation of the tensor that has this geometric significance. But looking at the map of eigenpolarizations, the different projections for different directions, is rather complicated. So if we look around these optic axes, and I can, so uniaxial is the more common one, then you can imagine as I vary a uniaxial object such as this, looking very close, an angle's very close to the optic axis, you always get the projected ellipse is going to either be radial or azimuthal. So this is the pattern of eigenpolarizations around a uniaxial optic axis. And looking at calcite between cross polarizers gives a pattern such as this. These black lines are where the polarizers here are vertical and horizontal, and so they block out when these polarizations are vertical and horizontal. A biaxial crystal has a slightly different structure, rather more complicated, coming from, well, here's an example of a biaxial object. It's just a chalk box. So what we're looking at is the direction where the projection of this looks like it's a square. And as I move around close angles to that, I'm looking at the long axis of the projection of the box for angles very close to the projection where it looks like a square. And it turns out I get a pattern that looks very similar to these confocal parabolas. And that gives rise to these sorts of patterns when you look through cross polarizers at an axis like this. Rather than having this cross, as we saw before, now I've just got this straight line because those verticals and horizontals now only occur twice around this optic axis, rather than here they occur 4 times. And again, I can do a demonstration to show you this, because it turns out there's a very common, or at least used to be very common, birefringent material that we all used all the time, namely overhead transparency foil. The way that overhead transparency is stretched, it's stretched in 3 different directions as it's manufactured, and so putting it between cross polarizers, it's easier to see, maybe if you come up afterwards, but if I move the angle around, this worked before, I'll have to show you if you're interested. Oh, there it is. Can you see?
Yeah, exactly.
So I have to find the angle. It's a little bit distorted, but you can see that sort of London Underground symbol, which is characteristic of this black line, this so-called brush, through the optic axis. But of course, overhead transparency, we don't normally see that polarization, otherwise it would have made lectures in the old days even more confusing. Not to say that they wouldn't be confusing these days, because we're surrounded by polarized light and we don't even realize it. Our eyes can't distinguish the fact this white is made up of perpendicularly polarized green and magenta. Okay, so these 2 rays are called, well, they're just called ordinary and extraordinary for historical reasons. But why do they separate as they propagate through the crystal? Well, of course, the ray direction, what we actually see, corresponds to the direction of energy flow, not the direction of the wave vector. And the energy flow is perpendicular to E, not D. E is tensorially related to D, so if D is perpendicular to S, and this is the optic axis of the crystal, at least for uniaxial, that means that E would be in this direction, which means that the propagation of the ray is perpendicular to it. And the two different images of under this mapping give us two different directions of the ray. And you often see people saying that the reason why they separate is because the refractive indices are different. It's not, it's because the direction of energy flow is different. So now we're in a position to see how people really think that Vikings might have measured polarization, measured their position, or the position of the sun with calcite. So the question is just, how can I use the calcite to, which is a uniaxial crystal, without a polarizer, to determine the direction of polarization? And the suggestion is that on the back face of the crystal, you mark a line that's perpendicular to the optic axis. So the optic axis is along this body diagonal, and I've marked this line here. And I rotate the crystal against the illuminating polarized light, and the intensity of these two images varies sinusoidally. So rotating the plane of incident polarization, the two images of this line that I've marked vary sinusoidally. And when this image is at a minimum, the marked line will then point in the direction of the polarization, and perpendicular to it will take you to the direction of the sun. Now, interestingly, looking at this picture, which is in reproduced in Ramskau's paper about Viking polarization, actually is the very first image of birefringence published in a book by Bartholinus, who was also Danish, so maybe this was a folk memory or something. And again, you can see this line going to these two lines here is exactly the idea going on, although Carlson's original method was using a dot, not a line, and turning it so he has equal intensity of his two images rather than one at a minimum. So these are various variations on the same thing. So here was the polarizer test out of the window, and here, I'm not going to try it now, I'll just embarrass myself. We can try it after my talk. Seeing it with the polarizer, the crystal, that was the direction towards the sun using the polarizer. Now using the crystal, and you can see these two lines, and the intensity is different, and it changes as we rotate the crystal. And I would say that's probably when it's at a minimum. And that direction is pretty much the same as the direction before. And there was no monkeying about between these two pictures. So and then this recent paper by Ropars et al., they claim, so they did very similar observations like this with setup, and they claim they're within a 1 degree error. Now, as I understand, if you're navigating, a 1 degree error can still be pretty fatal, but at least it shows that this method is pretty accurate. So that was all fun. Now I want to talk a little bit more mathematical about the actual work that I was involved in. This was actually not talking about the crystal polarization, it's talking about where this pattern in the sky comes from, which turns out to be remarkably similar to what we've already talked about. So this is the pattern of polarization in skylight if we could actually see polarization. Again, it's a fisheye lens, and these curves are sort of stream curves for polarization. So the tangent to the curve at each point would give you the direction of the linear polarization at that point. And you can see that they are pretty much perpendicular to the direction of the sun, but not quite. So looking a little bit more closely at the pattern, and this is an experimentally measured pattern by my colleague Ray Lee in the US Naval Academy, and well, he spent his life studying atmospheric optics, and so he says there's no coincidence that as a student of Rayleigh scattering, he should be called Ray Lee. But you can see that this pattern isn't quite this azimuthal pattern centered around the sun. In fact, the sort of pattern is centered more around this point and this point in the sky opposite the sun. Looking more closely at this pattern, it looks very similar to this set of parabolas that we saw before, and these are places where you can't determine the direction of the polarization because there is no difference as you rotate the polarizer. Historically, they're called neutral points, polarization neutral points. And this angle is about 15 degrees from the sun and rotates rigidly with the sun. So these points of no polarization lie in the principal plane that includes the sun and the zenith. Historically, the first one to be discovered was by Arago. It was about 200 years ago when polarization was a hot topic. Malus discovered polarization in about 1809, and so I guess in those days everybody was turning polarizers around, looking at everything they could, looking to see phenomena that they could get into their analog of PRL, and Arago discovered this direction in the sky about 15 degrees above the point in the sky opposite the sun, so it's only above the horizon when the sun is low, was a place where the polarization vanished. About 10 years later, Babinet discovered this one above the sun itself, a lot harder to see because the sun sort of saturates your eye. And when the sun is sufficiently high in the sky, the Arago point sets, but opposite it in the sky, a point rises, which was discovered by David Brewster in the 1850s. So these neutral points are about 15 degrees from the sun direction. And if we were to plot the polarization lines near the sun, we see these two nice topological disclination-like points where the polarization rotates around by pi. Of course, the polarization can rotate around by pi. We're not interested in the vector direction. We're only interested in the direction modulo a sine. So this is the same as this. Just like a liquid crystal, and they look rather like liquid crystal defects. So what is the physics that's going on? Well, we're interested. What's happening in the sky is Rayleigh scattering. Rayleigh scattering by molecules in the air. So now we're dealing with a mixture of different polarizations. Light from the sun is unpolarized, meaning it's a mixture of all of these different polarization directions. But as we've seen, they have to be perpendicular to the direction of propagation. And when the direction changes upon a scattering, the new polarization has to be perpendicular to S primed rather than S. And it turns out, so long as you're sufficiently far from the scatterer, Rayleigh scattering implies that, well, you tend to polarize out of the plane of scattering, but really what happens is if we represented this by a matrix M, a density matrix for these directions of polarization, the new polarization matrix is just M sandwiched between the two line of sight projection matrices. So I take this matrix, which would be, say, 1, 1, 0 if the third direction is S, and now I've got S primed, I take 1, 1, 0, and I sandwich it between these two projection matrices. And that turns out to be the result of what happens when light is Rayleigh scattered. I said D prime, that should have been S prime, sorry. So with this approach, in the 1950s, Chandrasekhar worked out radiative transfer theory, a very complicated problem of system of integral differential equations for many, many scatters, or infinitely many scatters, in a stratified atmosphere where the thickness, the density of scatterers changes as a function of height. And one result, but it's only possible to get any results assuming that the Earth is flat. So the Earth is flat, and so it really is stratified in a Cartesian geometry. But it turns out that's a reasonable assumption because the optical thickness of the atmosphere, the mean free path of these rays, is about equivalent to the radius of curvature of the Earth. It wouldn't work if we were on Mars, where the atmosphere is a lot thinner and the curvature is a lot greater, but it works pretty well for the Earth. So what we've got again is this idea of this projection geometry now playing a role in the polarization of Rayleigh scattering. So we're looking at each point in the sky a mixture of all the different rays that are coming in from all directions and are mixing together to give us an ellipsoid at each point in 3 dimensions. Ellipsoid, which is the mixture of all of the E vectors. And then a ray scatters and it comes to our eye. But actually, we can, so just as we've seen before. But actually, if we're assuming that there's this horizontal translation invariance, then this ellipsoid is the same at every point in the sky. And what we're doing is we're looking at the same object translated so it looks like we're looking at it from different projection directions when we change our viewing direction. So there's a duality between what is scattered out from these points and what is scattered to what comes in to the eye of an observer. And it's just the same transformation that we saw before. So if I take an ellipsoid and I plot the major axis, for simplicity, the major axis of the projected ellipse, we can see the sort of pattern that comes up. So I'm only going to look at the major axis direction as a function on the direction sphere. So this is an ellipsoid. It looks almost circular, but it is an ellipsoid. Its 3 axes are vertical, horizontal, and coming out in the blue direction. And these lines, again, are these sorts of integral curves of polarization where the tangent is the direction of the major axis of the projected ellipse in the viewing direction. So you can see as we go around the sort of pattern that you get that agrees with more or less what the eye can see in terms of the projected ellipse. And just see that again. And what is this ellipsoid? Looks very thin and slightly elongated. Well, that just comes from the fact that light from the sun is almost completely, looks like completely flat coming in, but of course it's reflected back and forth a little bit in the sky, which stretches it out. But crucially, there's a symmetry breaking. There's a lot more scattering on the sides than there is up and down, and that's responsible for elongating the polarization in the vertical direction just a little bit, which gets magnified in this projection to give this rather big difference of these 2 points, which of course correspond to the neutral points. Looking along that direction, this projected ellipsoid would be circular. And so this is this ansatz, this very simple ellipsoid ansatz, compared with the measurements of Rayleigh. And you can see the lines really agree very well, are fitted from the observations of where the neutral points were. So just knowing where the neutral points are, the neutral points correspond to these biaxes, this u and v, whose symmetric product gives you the tensor, and then that then fills in to give the direction everywhere else in the sky. So it really is a sort of topological argument. From these 2 defects, we can try and infer everything else. This is the modulus of the absolute difference in degrees between the red observations and the blue curves. You can see it isn't perfect. There is some systematic error, but it's still a very good rough guess. And this is something that I did with Michael Berry and Raymond Lee, well, now several years ago. But it turns out it gets a reference every time somebody writes a paper about Viking polarization, because this is such a useful way of working out what the pattern of polarization in the sky is. So our topological ansatz gives the polarization direction information agreeing well with the observation. Now it turns out we didn't do it geometrically in this paper. We had a slightly more convoluted argument, which is interesting in itself. Rather than worrying about this 3D geometry, which is rather complicated, of trying to work out spherical trigonometry, we thought about direction in the sky using stereographic projection. So this direction S in the sky with angles theta and phi under the stereographic projection transformation is e to the I phi tan theta on 2. It gives us a complex number, capital Z, to distinguish it from height. So Z equals 0 is the zenith straight up, and Z equals infinity, the point at infinity to compactify the Riemann sphere is the point straight down. Mod z equals 1 is the horizon. So if we're interested in the sky, we're only interested inside the unit disk. And this is a nice conformal mapping. And in particular then, rotations on the sphere, as things go up and down, can be realized by unitary Möbius transformations. And if z1 and z2 represent opposite directions, z2 is minus 1 on z1 conjugate. I can also represent polarization using a complex number. That, as I've said, the polarization turns around by 180 degrees naturally, coming back to itself. So if I turn the polarization by half of the angle I've gone round on this argand plane representing it, I can represent the angle of polarization with the argument of a complex number. And the modulus of this complex number is the degree of polarization. How polarized it is obviously if it goes to 0, I can't decide what the direction of polarization should be. And normally the sort of zeros could look very complicated and rather anisotropic, and these are the names we give to these sorts of morphologies that show up in typical polarization patterns. But the skylight pattern seems to be a lot simpler than these complicated things that show up in general. So what do I have? I have a complex polarization mapping. I'm representing direction, and in each direction I have a polarization. So I've got a complex function of a complex variable, which I know has got 4 zeros, these 4 neutral points on the full sky sphere. So when I give this talk to students, I normally ask them at this point, can you think of a function, a complex function of a complex variable with 4 zeros? And sometimes I get an answer and sometimes I don't. But of course, for this audience, I can say that, of course, it's a quartic polynomial whose zeros correspond to these roots. And this quartic polynomial actually gives us a very similar polarization pattern. Again, it turns out this is exactly, this is translated into complex plane geometry is exactly our ellipsoid geometry from before. So we can now actually calculate these polarization streamlines directly as 1 on the square root of this sigma function. And if the sigma function is an analytic function, for example, just z, I get nested parabolas. If it's z squared, I get these confocal ellipses. And if I have 4 roots with this geometry, then I get, in fact, contours of an elliptic integral. So the argument is the Vikings would have seen polarization pattern, which is contours of an elliptic integral viewing the sky as the Riemann sphere. So where's the physics? I mean, does this hold up physically? Why should it be so simple? And this is something that my colleague John Hannay thought about. And he realized that one approach would be to think of this scattering problem as a perturbation series in optical thickness. And because the sky is rather transparent, the optical thickness is small. The sky is the atmosphere is thin. So the full radiative transfer theory of Chandrasekhar can be treated by an expansion in small t. And you always have this projection on each side in the line of sight, but in general the thing inside is also a function of s, the direction you're looking in. But then what he found was, if the sun is sufficiently above the horizon, and you're looking above the horizon, this scattering series up to second order is independent of s. And if the scattering series is independent of s, then it just looks like what we had before, and thus justifying this geometric ansatz, so this skylight polarization pattern. So here's what it looks like. First, looking at the intensity as and decomposing it into a sum of spherical harmonics. This is for the Hannay ansatz, but now building in this weak s dependence. The ellipsoid approximation gives you this. The analytic approximation gives you this. There's a slight problem with the horizon that you don't have with the ellipsoid. And here's the modulus of CL squared, the weighting in the in the angular number L for different values of L. Normalizing it a little bit more favorably, you can see that even here, L equals 2 completely dominates. It's almost all quadrupole. But we're interested in the polarization directions, and you can't represent those with the scalar spherical harmonics. Instead, you need to use tensorial spherical harmonics, such as the spin-weighted harmonics proposed by Newman and Penrose, which have an additional label S, as well as YLM, and S is a tensorial index representing, well, this is a spin weight. For us, it's effectively the rank, which is 2 for polarization. And if L equals S, these functions have very special properties, including the fact they can be represented as order S holomorphic functions. So if we're talking about our sigma, S is 2, and so these, we're dealing with a holomorphic function of order, oh, that should have been, they should have been 2S, sorry. That should have been, so we'd have quartic polynomial functions, which is exactly what we've seen before. So the spherical harmonic representation naturally explains why we should be seeing this quadrupole in the polarization pattern, because we don't see so much from these higher harmonics. And looking at the angular spectrum of the sky polarization, and here's the ellipsoid approximation compared to the analytic approximation, again, you can see that it's almost all in the L equals 2. So this is now from the Hannay approximation, almost all of it favors the L equals 2 mode, thereby giving a sort of account for why this ellipsoid really appears in the skylight polarization. And so we were very pleased that we could go back now to David Brewster, who of course is very well known for his work in crystal optics, and he also worked in the skylight polarization. In fact, he wrote this: "It is not one of the least wonders of terrestrial physics that the blue atmosphere which overhangs us exhibits in the light which it polarizes phenomena somewhat analogous to those of crystals with double refraction." So the idea that biaxial ellipsoids not only are useful to describe birefringence of biaxial crystals, but also, strangely, in the skylight polarization, which allegedly the Vikings were measuring with those polarized crystals. And I leave you with this thought that, had we evolved to see polarization, maybe topology would have been part of the human story for a lot longer than the last 100 years. The fact that there are these defects in the sky that are visible to anybody who can see polarization is very striking. I think that, if we could have seen it, there'd be poetry about this pattern. There'd be mythology about it. There'd be love songs about it. But instead, it's left to science to reveal it. And of course, this is a slightly old-fashioned physics, but another polarized sky map that is getting a lot of interest at the moment is the cosmic microwave background. So this is the measurement of the temperature fluctuations of this microwave radiation coming from the Big Bang. And the satellite that was doing the measurements about 10 years ago, the WMAP satellite, had some rudimentary polarization sensitivity. So you can see these are a very low angular resolution, the directions of the polarization in the sky. And one of the main objectives, as I understand, of the Planck mission, the mission that is currently measuring this pattern at a far higher angular resolution, is to try to get a better idea of what this polarization pattern looks like, which comes to us not in the light coming from scattering in our atmosphere, but from the early universe. And this is a sort of simulation that is beginning to appear in papers about this subject. So, in conclusion, the blue sky has a polarization fingerprint pattern, which is seen and used by creatures mainly with non-mammal eyes. We've had a quick tour through crystal optics and scattering theory, seeing how many concepts followed simply from the idea of the geometry of three-dimensional ellipsoids. Using a uniaxial birefringent crystal such as calcite, we've seen how the polarization direction may have been measured by Vikings using sunstones. And hopefully more interesting, we've seen that the skylight polarization pattern is close to that of a biaxial crystal, where the optic axes are the same as the neutral points, and it's all revealed in a nice tied-up way by three-dimensional and argand plane geometry. Thank you very much.
Oh, thank you. Really. I think your students at Bristol must be pretty bright to take all this in. A lecture to undergraduates. Very good. Any comments? Conrad?
Yeah, so what would be the algorithm for a bird to determine position of the sun when it's completely overcast?
So I think the argument is if it's completely overcast, then you can't do it. The one thing is if there's a small window of blue, or indeed if there's still some blue in the sky and the sun has set, then any small patch of blue would reveal this pattern, and then you could figure it out. So yeah, it's not perfect, but you need some visible blue sky.
So nothing.
Well, okay, so
this information comes through the.
So that's right. There's a lot of multiple scattering inside the cloud that completely depolarizes the light. Now, the paper that I showed the title of by Horvath and co-workers was wondering whether indeed there is enough residue of this polarization coming through either fog or clouds, and they see something with modern polarimetric devices, but whether the eyes of the birds or indeed the Vikings could have detected that, I'm not sure. I'm speaking to biologists who talk about animal sensitivity to polarized light. They say that that they do see a difference in behavior in animals when the sky is completely overcast.
So I was at the Natural History Museum last week, and they have a massive block of birefringent crystal with a mark on the back that you can see in two places on the front. But have you ever suggested to them that they put a polarizer up as well?
Well, okay, so I haven't spoken to them in the Natural History Museum. I can say that a lot of popular public understanding of science museums do have this. I know that there's actually a rotatable polarizer in the museum in San Diego, for example. So the Natural History Museum is perhaps an anomaly. Though it is interesting that, in saying that animals have this polarization sensitivity, some trilobites, supposedly in their eyes with lots of lensless arrays, actually had calcite. They somehow biologically synthesized calcite as these lenses. And so when it was fossilized, those lenses remain. And there are photographs in the papers that study these eyes taken through these birefringent crystal eyes that, from millions of years ago, and can still see through those eyes.
Wow. So what's the biochemistry of the bird eyes that can see polarization? I mean, what are they?
Well, so our eyes would be able to see it as well. The idea is that the cones that detect mainly color are slightly, if they're slightly elongated, they're sensitive to one polarization more than another. And that tends to happen anyway in our eyes. It's just that the pattern formation of these cones on the retina is sort of randomized and it messes it up. Now, the fact that there is some slight pattern arrangement in the different colored sensitivity of these cones is what gives us this residual hiding a brush sensitivity that some people have more than others. But the question is then, is that because of pattern formation for other sorts of embryological reasons in our eyes, or is that because we actually evolved at some point to see polarized light? And I don't think anybody knows.
Can I come from another universe and ask you about why you get a quartic? So somehow I missed the mathematical logic. So you have a quadratic differential. You have this line field.
So I sort of skipped some of the obvious things because I wondered whether it was too obvious. So the main thing is that
Thank you. Carry on.
is that we're talking about these natural defects in these line fields, which naturally have a sort of Poincare Hopf index of 0.5 rather than 1. So because we're drawing a line field on the sphere, we have to somehow accumulate the Euler characteristic of 2 for the sphere.
No, I understand.
So we have to have 4. If we're going to have, if all of the
Yeah, but there's lots of line fields on the sphere with many singularities of many different.
right, but then what are the simplest ones? The simplest ones are going to be the ones that still have the 4 and no other ones. So if you were to look at, so the key is in these spin-weighted spherical harmonics. So it turns out these spin-weighted spherical harmonics correspond to different lines of the irreducible representations of the rotation group SO3. So usually the spherical harmonics are the central column in the representation matrix. Now, when we move off, we get these other things. And these are the basis functions if you want to represent these line fields on a 2-sphere. And so, in general, any pattern that you get, you can decompose using these.
It's the lower order spherical harmonic representation.
So the lowest order spherical, and there's this theorem that says that the lowest order spherical harmonic representation is effectively holomorphic. So this S of spin 2 corresponds to this 2-fold rotational symmetry. If I had a 3-fold or a 4-fold or a 5-fold rotational symmetry, I get a different sort of holomorphic function representation. There's a different way of accumulating enough zeros and no more to give us the Euler characteristic of 2.
How are they defined, these functions, the S, Y, L, M?
Well, as I say, you get them from, I mean, they look, they're using, you use Jacobi polynomials rather than the Legendre polynomials.
Oh.
So the easiest way of getting them is from the irreducible representation matrix of SO3, which is how you get one way of getting the spherical harmonics as well. They have so rather than just having L and M, we also have this extra S label, and that just tells you S would be 0 for a spherical harmonic.
Yeah. Hmm. Okay, well, there we are. Let's go out and look at the blue sky.
Yes.